Pocas universidades en el mundo llevan el nombre de todo un país. Esta es la Universidad de Chile. Su nombre es reflejo de una misión y un compromiso: guiar el desarrollo de Chile en conexión con los grandes desafíos globales. Investigamos el origen de la vida en laboratorios naturales únicos. Buscamos respuestas y soluciones para hacer posible un mejor futuro, sin importar las distancias ni los obstáculos, trabajando en conexión con la sociedad a lo largo y ancho de esta tierra de extremos y contrastes. Somos la Universidad de Chile. Estamos en el corazón de este país, vinculando ideas y personas para conocer nuestro pasado milenario y avanzar en la comprensión del universo. Contamos con la mayor infraestructura universitaria de Chile, distribuida en 5 campus y múltiples otros recintos dedicados a la formación, la investigación, la creación y la vinculación con la comunidad. Aquí se preserva y fortalece la más amplia red artística, cultural y patrimonial de nuestra nación. Somos la principal universidad del país y una de las más importantes de Latinoamérica. Lideramos la producción científica nacional en todas las disciplinas, con investigaciones que destacan con el nivel de impacto más alto en toda la región. Esta es nuestra casa y la de todos los chilenos y chilenas. Aquí trabajamos para hacer realidad nuestros sueños y aportar un legado de prosperidad para el mundo, ampliando los límites del conocimiento y la creación. En estas aulas, bibliotecas y laboratorios e incluso en algunos de los lugares más extremos del hemisferio sur. Formamos a los profesionales y especialistas que han construido esta nación y a intelectuales que han trascendido nuestras fronteras como referentes internacionales de la ciencia, la cultura y las artes. Unidos en esta diversidad de paisajes, colores, personas e ideas, construimos una comunidad sin fronteras. Juntos, desde múltiples disciplinas, estamos comprometidos con los grandes problemas de la humanidad, conectados para desplazar los límites del conocimiento y forjar nuestro futuro, derribando todo tipo de obstáculos. Trabajamos desde Latinoamérica en alianza con las principales universidades y centros de investigación del planeta. Esta es la Universidad de Chile, una comunidad vinculada con el mundo para formar, investigar y crear en conexión con los grandes desafíos globales. La universidad, donde se vive la experiencia de todo un país. Pocas universidades en el mundo llevan el nombre de todo un país. Esta es la Universidad de Chile. Su nombre es reflejo de una misión y un compromiso: guiar el desarrollo de Chile en conexión con los grandes desafíos globales. Investigamos el origen de la vida en laboratorios naturales únicos. Buscamos respuestas y soluciones para hacer posible un mejor futuro, sin importar las distancias ni los obstáculos, trabajando en conexión con la sociedad a lo largo y ancho de esta tierra de extremos y contrastes. Somos la Universidad de Chile. Estamos en el corazón de este país, vinculando ideas y personas para conocer nuestro pasado milenario y avanzar en la comprensión del universo. Contamos con la mayor infraestructura universitaria de Chile, distribuida en 5 campus y múltiples otros recintos dedicados a la formación, la investigación, la creación y la vinculación con la comunidad. Aquí se preserva y fortalece la más amplia red artística, cultural y patrimonial de nuestra nación. Somos la principal universidad del país y una de las más importantes de Latinoamérica. Lideramos la producción científica nacional en todas las disciplinas, con investigaciones que destacan con el nivel de impacto más alto en toda la región. Esta es nuestra casa y la de todos los chilenos y chilenas. Aquí, trabajamos para hacer realidad nuestros sueños y aportar un legado de prosperidad para el mundo, ampliando los límites del conocimiento y la creación. En estas aulas, bibliotecas y laboratorios e incluso en algunos de los lugares más extremos del hemisferio sur. Formamos a los profesionales y especialistas que han construido esta nación y a intelectuales que han trascendido nuestras fronteras como referentes internacionales de la ciencia, la cultura y las artes. Unidos en esta diversidad de paisajes, colores, personas e ideas, construimos una comunidad sin fronteras. Juntos, desde múltiples disciplinas, estamos comprometidos con los grandes problemas de la humanidad. Conectados para desplazar los límites del conocimiento y forjar nuestro futuro, derribando todo tipo de obstáculos. Trabajamos desde Latinoamérica en alianza con las principales universidades y centros de investigación del planeta. Esta es la Universidad de Chile, una comunidad vinculada con el mundo para formar, investigar y crear en conexión con los grandes desafíos globales. La universidad, donde se vive la experiencia de todo un país. Pocas universidades en el mundo llevan el nombre de todo un país. Esta es la Universidad de Chile. Su nombre es reflejo de una misión y un compromiso: guiar el desarrollo de Chile en conexión con los grandes desafíos globales. Investigamos el origen de la vida en laboratorios naturales únicos. Buscamos respuestas y soluciones para hacer posible un mejor futuro, sin importar las distancias ni los obstáculos, trabajando en conexión con la sociedad a lo largo y ancho de esta tierra de extremos y contrastes. Somos la Universidad de Chile. Estamos en el corazón de este país, vinculando ideas y personas para conocer nuestro pasado milenario y avanzar en la comprensión del universo. Contamos con la mayor infraestructura universitaria de Chile, distribuida en 5 campus y múltiples otros recintos dedicados a la formación, la investigación, la creación y la vinculación con la comunidad. Aquí se preserva y fortalece la más amplia red artística, cultural y patrimonial de nuestra nación. Somos la principal.
Muy buenos días a todas y todos quienes nos acompañan en esta jornada en el diálogo con el profesor John Sonntag, el rol de la ingeniería en la ciencia moderna polar, en un trabajo coordinado
in a
entre
coordinated
la
work between the University of Chile, together with the U.S. Embassy and the American Spaces Network. This dialogue with the engineer will give you details about his time as part of the Airborne Topographic Mapper team of NASA in 1993, when he started working as an engineer with his team. He published and operated and discovered scientific discoveries using laser mapping technology installed on airplanes. Sonntag in 2002 started an association with the Center of Scientific Studies, SEX, and the Chilean Navy to keep studying Antarctic ice. That means that in 2009 we started the Ice Bright operation from NASA, which in 11 years they flew around 11 times over the Antarctic, using as base of operations the city of Punta Arenas. Some of those flights even reached the South Pole. This 2-decade-long work finished in 2021, and he wishes to share his experience with you. Next, we would like to invite Professor John Sonntag to the podium. Muchas gracias a todos por venir, a ambos que están aquí, y a los que están aquí y los que pueden estar en línea. Creo que Dice, puedo ver la pantalla mejor desde aquí, así que probablemente lo voy a hacer desde acá. Entonces, como la presentadora dijo, me gustaría hablar con ustedes acerca del rol de la ingeniería, tecnología y adaptabilidad, me refiero a adaptabilidad personal, en la ciencia polar. Lo que planeé discutir hoy día y mis declaraciones preparadas son principalmente acerca de mi trabajo. Fue un trabajo bastante inusual y pensé que sería interesante y quizás útil para algunos de ustedes que quizás quieran seguir alguna carrera similar haciendo ciencia en terreno. Quizás podría ser interesante escuchar de ello. Así que no planeé
but I do hope that you'll feel free to ask any questions you might have about that. I can't promise I can answer all of them, or even many of them, but I'll do my best. A friend of mine at NASA, Goddard Space Flight Center, tried something on ChatGPT a couple of weeks ago, and I thought it was amusing. I wanted to start off this chat by showing you what that looked like. You can see what he typed in as a search term at the bottom of the page there. He wanted to see what artificial intelligence thought that doing airborne science in the polar areas looked like, and that's what they came up with. We both got a good laugh out of it at the beginning. There's a lot of sort of silly things on there, and there's a little bit of truth, too. The first silly thing that I noticed is the people in the white lab coats. I've been a scientist for 30 years, for 3 decades. I've literally never worn a white lab coat in my life, ever, so that's pretty clearly wrong. Also, the way those airplanes are flying so close to those mountains is not safe at all. I would, if it were me, I'd file a complaint against those pilots at my first opportunity because I think they're about to kill somebody. Some of it's right, however. You see lots of people gathered around computer screens and laptops, and that happens all the time. Where you're looking at weather maps or you're looking at the dreaded email from your boss back home. So that at least it got correct. But most of that's really kind of wrong, and so I'm hoping to tell you a little bit more of the reality of scientific field work today. Okay, here's what it's like, at least what it's like for me for the last 3 decades. A lot of my friends, particularly the people who aren't involved in science back home in the United States, they think that being a NASA scientist is a glamorous thing to do, and I can tell you it's not, at least not very often. You're going to get dirty if you do it, and you're going to get dirty quite often. That's a normal daily routine. I myself, as part of my job, have had to clean toilets, for instance. I've cleaned kitchens. I have used solvent on hydraulic bays at in the bottoms of airplanes so that the hydraulic oil wouldn't get on the optics of our instruments. You do whatever you have to do when you're in the field to keep something going. And honestly, that may sound terrible. It's actually part of the fun. At least I found it that way. And along with that, you're going to get smelly. I think I just explained why that's the case. Privacy is something you almost never have, and that's particularly the case in the polar areas where every bite of food, every tent, every building that you might stay in or sleep in, every bedroll, everything has to be brought in from very far away. And so everything is scarce, everything is expensive, and you have to make do with what you have, and that includes the space that you sleep in and that you live in. I've had projects, particularly here in Chile. I've always been grateful for this, where I've stayed in very nice hotels, but that's rare. Most of the time, we stay in pretty bare lodging. I've even had to build my own igloo in Antarctica and sleep in that for some of our field projects. So again, not always so glamorous. Let's see. Things surprise you all the time, every day, and that's both part of the frustration and also part of the fun of airborne science. Something new hits you all the time. It might be politics. It might be something breaking. It's very often the weather. It's somebody that you work with. It's often, again, that dreaded email for back home that will surprise you and tell you have to do something that 5 minutes earlier you hadn't dreamed of. So that's part of the deal. And again, it's part of the fun. It keeps you on your toes. It keeps you smart. It keeps you sharp. Let's see. Airborne science and field work is also the most rewarding thing I've ever done. I've just given you some negatives of it, but the negatives also tend to be the positives. There's really nothing in the world, dealing with small children may be an exception, but other than that, there's really nothing in the world that keeps me sharper, makes me feel smarter, and sometimes makes me feel dumber than airborne science field work, because it always challenges you. But because it challenges you, it tends to bring out the best in you. It also brings out the best in the people that you work with. And one thing I've found over the 30 years that I've done this sort of work that used to surprise me and doesn't surprise me anymore, because I've come to conclude it's just part of human nature, that it's when the conditions are the worst, when you're working in the most extreme cold, or maybe the most extreme heat, when you're working the hardest, when you're working the longest hours, when your bosses are being as hard on you as they ever be, those are the times that brings out the best in both you and your colleagues. And those tend to be the most rewarding times. It's when the group of you work together best as a team, is when you're on under the most difficult conditions. It really does bring out the best in humanity. And it's also the most fun thing I've ever done. It really is, for the same reasons I just told you. I don't do much of it anymore. Icebridge, as you've been told, ended about 2 years ago. So I don't do as much field work as I used to. I still get to do some, and I look forward to it. But the camaraderie and the accomplishment of field work is something that I miss, and I hope to get to more of in the future. Okay, so I wanted to tell you a little bit more about what scientific field work is like, and I wanted to start before myself. The person in the center of that photo is somebody when he was old and I was young, I was lucky enough to meet him. His name is Charlie Bentley. He is an American geophysicist. He ended his career at the University of Wisconsin. But what Charlie became famous for, rightly so, was during the International Geophysical Year of 1957. Charlie spent, I believe it was 25 months on the ice of Antarctica. He spent over 2 years there. And when he started, what he did, Charlie was a seismologist. So he used sound waves to study the interior of the Earth. That was his job. And when he started in 1957, and mind you, most of you are much younger than I am, but 1957 was just a few years before I was born. This is recent history. When he started, essentially everybody thought that the world's great ice sheets in Greenland and Antarctica were basically thin layers of ice on top of high plateaus, high rocky plateaus and mountains. Well, Dr. Bentley proved that wrong, and the way he did that was by using technology. What he would do was he would set off small explosive charges. Some of you may know this topic better than I do, by the way. I'm not a seismologist. But he would set off small explosive charges on the surface of the ice sheet, and he set up arrays of sound sensors. And he would time the time elapsed between the initial explosion on the surface and the time when the echoes had traveled through the ice, bounced off the bedrock, and came back to the sensors on the surface of the ice. From that, and knowing the speed of sound and ice, he could determine the thickness of the ice. And what he found was astonishing. It surprised him and everybody else at the time. So instead of the West Antarctic ice sheet, which is what he was studying at the time, being just a thin layer of ice on a rocky continent, basically West Antarctica was and is a mountain of ice. It's several kilometers thick. And in fact, it's so thick that the bedrock was actually, in many places, most places in West Antarctica, below sea level. And that has profound implications for the ice's future and our future as a species. The reason I wanted to tell you about Charlie and his work just 10 years before I was born is because Charlie was trained as a geophysicist. He knew the theory of geophysics. I didn't know Charlie well enough to have a good long conversation about exactly how he was trained, but I'm fairly confident that he was not trained as an electronics technician. But the instrumentation you see here is very similar to what Charlie would have used in the late 1950s during the IGY. The point I'm trying to make to you is that as a scientist, young and old, if you go in the field, you're likely to find that you'll be called upon to do many more things than what you were trained for. You may know astronomy, you may know geophysics, you may know particle physics, but whatever you know, I can guarantee you will be called upon to tackle things that you didn't expect to tackle. Cleaning toilets, for instance. Luckily, that doesn't happen very often. But being an electronics technician, being a computer programmer, being a weather forecaster, all kinds of things that you didn't expect. So adaptability is extremely important if you want to be a field scientist. It's really important in your whole life. But from personal experience, I can tell you it's extremely important as a field scientist. This is a little more like the work that I did. These photos were taken aboard an Armada de Chile P-3 patrol aircraft in 2002. You guys were told about that before I came to the podium. This is about 10 years into my career, where my managers at NASA and folks down here in Chile came up with a very innovative arrangement to study ice in Antarctica. At the time, this was shortly after my team at NASA had just published the very first assessment of the mass balance of one of the world's major ice sheets. I had a boss at the time, and he used to enjoy telling people that when we started that work in the early 1990s, we didn't even know the sign, plus or minus, of the mass balance of the world's major ice sheets. We didn't know if they were growing or shrinking, and that's just 30 years ago. That's not very long ago. But by 2002, we did know that in the case of Greenland because we'd measured it directly by flying crisscross patterns in a NASA aircraft over Greenland. So naturally, the next thing we wanted to do was to do the same thing in Antarctica, but that's a lot harder sell to NASA management. Getting an airplane to Greenland is one thing, getting an airplane to Greenland is a lot more expensive and difficult proposition. And we couldn't convince them to do that, at least not at first. So what we did was we reached out to our friends in Chile, in the Armada and at the Centro de Estudios Científicos de Santiago, and came up with a very innovative partnership where the aircraft was already here. It's already pretty close to Antarctica. And so we outfitted it with mostly NASA, also some Chilean scientific instrumentation. We deployed the aircraft to Punta Arenas, and we staged about a half a dozen flights that first year out of Punta Arenas to West Antarctica. And what you see here is some of the hardware and some of the people that did some of that work. And this is later. These photos are just from the last few years, last couple of years. They are some of the instrumentation that I myself built over the years, and also some of the software that I wrote. And again, the point I'm trying to make to you here is whatever you choose to do in your scientific career, again, you're likely to be called upon to do things that you don't anticipate right now. I became a software developer. I didn't know anything about developing software when I got out of college. I knew how to write a program, and that's about it. But I had to learn that because I had to write software that would guide airplanes past the North and South Poles, because nobody else had ever done that. That was new. And so that's the thing about science. The whole point of science is to do new things, things that the manufacturers have not come up with ways to do, and so you will be called upon to do them. Okay, I'm having a little bit of trouble reading that from here. Let me see. Okay, I wanted to talk just a little bit about the skills, the particular skills that were needed for the work that I did, because I think these will not be identical to whatever you do, but they'll be, I think, representative. Of course, there's the foundational scientific discipline that you have chosen to study, astronomy, geophysics, whatever that may be. As you know, I'm sure very well, computer technology is a big part of everything that scientists do. And so not only using computers, but also programming them to do the things that you need them to do. So software development is a big part of it. As I mentioned, electronics, being an electronics technician is a big part of scientific fieldwork. And maybe I should back up just a little bit and point out that even in a very, very rich country like the country I came from, we cannot convince our managers to send all the people into the field with us that we need to do all the work that we need to do. We're not that rich. So what that means is that as individuals, we all had to learn to do all kinds of things. So I was trained as an aeronautical engineer. That turned out to be a relatively small part of what I did during my 30-year career. Electronics technician was a big part of it, and in fact, I'm hard-pressed to think of anybody I worked with in the field that didn't have to do a fair amount of electronics technician work. So that's part of it. Mechanical design, that's very important. If you, when you design an instrument that needs to fit in the belly of an aircraft and be subjected to sometimes many G's of force, the mechanical design of that system and the way that it's connected to the aircraft is obviously very important. We don't want anybody to get hurt. We don't want the airplane to crash, obviously. And that means that mechanical design is a big part of what we do, whether we're trained in it or not. Let's see, meteorology, that's one of mine. Again, I studied aeronautical engineering when I was young, when I was at university. And it never even occurred to me that I might need a meteorological background in my later career. But again, we couldn't afford to bring a trained meteorologist with us, so that became one of my jobs. And it turned out that a course of study in aeronautical engineering turned out to be, to my surprise, a pretty good backdrop for meteorology, because both fields use thermodynamics, or basically the basis of both fields. The way that air flows over a wing, through an engine, or across a mountain range is actually very similar, and the math that describes those phenomena is also very similar. So I applied myself to learning that, and actually had quite a good time with it. It turned out to be a lot of fun. Knowledge of aircraft operations, that's probably pretty obvious from the work that we do. You have to understand what airplanes can, and especially what they can't do, what their limitations are in terms of range. You also have to understand the constraints the air crews deal with. They can't work forever. They can only work so many hours before they become tired. And there are rules governing that. We can't break those rules, and that's for our own safety. And so you can't properly plan and execute a airborne scientific mission unless you understand those constraints. Geodesy and surveying, that's one of the things I was trained in, and that's part of a big part of what we did in the field. In fact, you can see the photo there is of one of my colleagues. His name is Kyle, and if you look carefully, you can see a strange thing on the top of that car. That's a GPS antenna. Some of you probably know that. And one of the things that we had to do wherever we went was to survey a big open area. Usually it was an airport ramp. Oh yeah, thank you. That helps. Can you guys hear me? Yeah, that's better. Thank you so much. So we had to survey things like parking lots, airport ramps, and then we would fly our instruments over those, usually every day, and we would compare what our instruments told us about that area with what we measure on the ground here with that vehicle. So understanding things like surveying and geodesy were very important. Navigation was another thing that I learned then, and I'm still doing now, even though I'm getting a little bit closer to retirement. That turns out to be a very important thing for NASA. If you take an airplane from here to Iquique, it doesn't really matter that much if the airplane is half a kilometer off to one side, but NASA cares very much because we have to put our instruments exactly where they need to be in the air, and often that means the instrument needs to be literally within a meter or two of where we need it to be in order to collect the measurements. That means very precise navigation is extraordinarily important to what NASA does. And again, because that is such a niche field, because there's almost no commercial need for it, there aren't industries out there that build these kinds of systems. So it falls to us that aren't particularly trained in these things to learn to do it ourselves. And that's one of the real joys of a career in science, at least I found, and that surprised me, is that you're often called upon to do things that you don't know how to do, and you've got to figure it out. Diplomacy. When you fly an aircraft to Chile, to Greenland, to Antarctica, to Argentina, to Svalbard, to Alaska, to wherever you are, you're going to find that you need a lot of things that you didn't bring with you. You need to feed your crew. You need to provide them with lodging. You might need to keep the airport open past its normal hours of operation. You might need all kinds of things. And while we can often pay for those things, sometimes we can't because there's just not a financial mechanism to do so. And that means you basically need to be nice to people. You need to be a decent human being, and you need to approach the airport manager, or you need to approach the grocery store manager, or whoever it is that you need something from, and convince them that what you're doing is important and to help you out. And again, just being a decent human being and learning a little bit of diplomacy is a part of that. As you can imagine, leadership is a big part of it. We'll talk about that more in another slide. Successful field teams. Obviously, we need specialists in many fields, but as I said, we usually don't have them, so we have to become the specialists ourselves. And that's where the generalists and the problem solvers come in. I'll go back to Kyle here. Kyle had a bachelor's degree in, I think it was physics, from a small school in the eastern part of the United States. He had essentially no direct knowledge of the things that we did in the field, but Kyle is a problem solver. You could throw literally anything at Kyle and he would come up with a solution. And a person like that, regardless of the fact that he wasn't directly educated in these things, was almost literally worth his weight in precious metals to have in the field. Because somebody like that, a leader in one of these field programs is presented with a dozen problems every day that he doesn't necessarily know how to solve. So having a person that you could depend on to solve those problems, or more than one person, as we were often lucky to have, is extremely important. Obviously, your leaders need to understand the basic scientific questions that are addressed, and that's why the fundamentals of what you're learning now are again of fundamental importance. Of course, you know that to anything that you're going to pursue later. But the best leaders also need to understand both the problems their people are working with and also the people themselves. I think that's probably pretty obvious, but that's not obvious to a lot of leaders. And so if you want to be a leader, I think it's important that you understand that again, you need to broaden your point of view and get to know your people. And most importantly, I've been on teams that weren't very functional, but mostly I was very lucky in my career. I've been on very highly functional, very effective teams. And what the things that characterize them are not only that they know their jobs, but they also like each other. They live and they dine and they play together. As you can see in the photo here, some of my friends and I are out on a run in Greenland together. And that is extremely important. It builds camaraderie, it makes people depend on each other, and makes people trust each other. My own path, I can tell you just a few more details on that. A photo here of myself and my colleague Michael Studinger. He was actually the one that came up with the ChatGPT slide early. We're in the weather office in a place called Kangerlussuaq, Greenland, in southwest Greenland, chatting with a Swedish meteorologist about the weather we could expect over Greenland that day. My university degree, again, was in aeronautical engineering. I had a master's in aerospace engineering, so I moved a bit from airplanes to designing spacecraft and space missions. That turned out to be almost ideal for my later career because I had to work both with airplanes and with spacecraft literally every day, so knowing something about both of them was a tremendous amount of help to me. I was pretty lucky in that regard, really. Most of the people that I work with that weren't lucky enough that the things they studied in school were directly applicable to what they did in later life. For me, it was. I was just very lucky. NASA had a team that began in the early 1990s, about the time that I got out of graduate school. The team was called the Airborne Topographic Mapper team, ATM, and I joined them mainly as a GPS analyst. My job was to sit behind a computer and analyze GPS data. At that time, that was a very new thing to do. But I wasn't satisfied with that. I wanted to go have some adventures too, so I insisted that I go out in the field with the teams on the airplanes. And in the process, I was able to learn all aspects of polar science campaigns firsthand, with firsthand experience. During that, one of the things I found right away was we identified a very deep need for deep knowledge of meteorology, and I applied myself to learning it. So we're speaking to a professional meteorologist there, and that was extremely valuable. We couldn't have done what we did without their help, and that was also the true here in Chile. We depended very much on the Chilean meteorologists for the work we did with CECS and the Armada, and later work as well. However, professional meteorologists they know how to help a pilot get an airplane from New York to Los Angeles or from Santiago to Iquique. They're not very familiar with somebody who wants to do something kind of crazy, like fly an airplane at just a few wingspans above the surface of the ice. They're not familiar with the weather there. So it was important not only that we work closely with them, but that we also educate them in what we needed. And the woman's name there is Veronica. She worked with us for many years and became very, very knowledgeable about the things we needed and the things that could affect our scientific productivity, and became a very useful member of, not directly of our team, but we thought of her that way, and she's still a friend. As I said, I also needed to learn a lot about navigation. A lot of that is a very obscure topic that literally just a few dozen people in the world know about, because there's not that much need for that level of knowledge, but in NASA, we did need that, and so I had to learn it. I helped lead Operation Icebridge from 2009 to 2021. I was flight planner, the navigator, the meteorologist, electronics technician, all the things I've already told you about. Right now, Operation Icebridge ended 2 years ago, and so what I'm doing now is I'm moving slowly towards retirement. I still consult with NASA. My main job is to work on improving the technology that we developed during Icebridge for further NASA missions, and also on operations itself. So NASA has a new project. It's much smaller than Icebridge, but it's going to Greenland about this time next summer. And my job with that project is to try to help them to not make the same mistakes that we did with Icebridge, with aircraft operations in the poles. From here, I just wanted to show you all some photos of our work, and also talk just a little bit about the science. What you see here is a small Piedmont glacier that's emptying out from a plateau in northwest Greenland. This is not one of the big glaciers in Greenland. But the reason I wanted to show it to you is you can see around the sides and around the bottom here, these rock piles. Those are the moraines. The ones at the bottom are called terminal moraines. The ones at the sides are called lateral moraines. It's a French word because of the Alps. They're experiencing the Alps. And what you see over and over again around the edges of Greenland is a picture very similar to this, where the glacier has receded, quite obviously, hundreds of meters or sometimes even kilometers from the moraines its earlier self bulldozed out. That means the glacier is getting smaller. The rocks don't melt, but the ice does. And so literally everywhere you look when you fly around the perimeter of Greenland, you see this visually with your eye, this very obvious signs of change and the glacier's receding. This is Petermann Glacier, also northwest Greenland. It's actually the bay that leads into Petermann Glacier. You can see the characteristic cracks in the sea ice there on the surface. It's blowing snow that you're seeing. There's a very strong wind coming off that cliff and blowing snow off the surface. I'd mentioned it's important to have knowledge of meteorology and aircraft operations, and this photo is a good example of that. When you fly in a situation like that, you get bounced around pretty badly, and you can hurt people, and you can damage your airplane, you can damage your instruments. So that day, I was not particularly good at avoiding that particular situation. But normally, that's something that we do, is we look for very windy situations like that, where the wind is strong at the surface, and try to avoid them. Just a pretty picture of a couple small glaciers at this time, the very south end of Greenland, a particularly calm fjord. Again, it's hard to find calm conditions on Greenland. It's a pretty windy place, but that day it was, and a very, very beautiful spot. This is at the other end of the Earth. This is the Shackleton mountain range in East Antarctica at sunset. This is Pine Island Glacier in West Greenland. This is one of our primary targets when we flew with the Armada de Chile and CECS in 2002, 2004, 2009. Pine Island Glacier and its neighbor Thwaites Glacier lie just a little bit south and west of a long way south and west of Tierra del Fuego. But we could reach there with NASA aircraft and also the Armada aircraft. I took this photo in 2018, and that was at a time when a very large iceberg had just broken off the Pine Island Glacier, and what you're seeing in there is the edge of that iceberg. One of the things that you find when you take photographs of the polar area is it's very difficult to get a sense of scale. How big are these things in your photo? You know, it's hard to tell if we're looking at a few feet or a few meters or a few kilometers. So just for scale there, our instruments told us at the time that those ice cliffs are about 60 meters, about 200 feet above the surface of the water. This is the Armada de Chile P3 flying above, I think it was Rothera Station on the Antarctic Peninsula with me on board and my colleagues on board in 2002. And that's that same aircraft flying overhead up over the southern ice fields in Chile. And my last photo, this is the formation of another very big iceberg. This one off the Larsen C ice shelf, which adjoins the Antarctic Peninsula. Larsen C is of a great deal of interest right now scientifically. The way that the ice shelves and the big ice shelves on the Antarctic Peninsula are named is there at least used to be a Larsen A, a Larsen B, a Larsen C, and a Larsen D. Larsen A doesn't exist anymore. It shattered and broke apart into it disintegrated in the year 1995. Larsen B, all except for about 10% of it, which is still left, did the same thing in 2002. That was the same year we first came down here to start surveying from the air. So Larsen C is the next one on the list. I probably didn't keep you in too much suspicion about that. So it's of a lot of scientific interest now to keep a close eye on what Larsen C is doing. So an ice shelf, in case you don't know, an ice shelf is what happens when a glacier flows into the ocean, usually with a lot of neighboring glaciers, and the ice starts to float and forms a big patch of ice that's floating. So when that ice shelf melts or when it shatters, it doesn't by itself raise sea level because it's already floating. The ice just melts and goes into the ocean eventually. However, what it does do, and this was prior to 2002 when Larsen B broke up, it wasn't known. It was another one of these big questions, big fights in the scientific community about, well, does a floating ice shelf, does it exert back pressure on the glaciers that feed it from uphill? And probably most glaciologists at the time thought that it did not. It was floating. You know, how much force could it really exert on the glaciers flowing into it? Well, we found out otherwise when the Larsen B broke up in 2002. The glaciers that feed it, of which there are a couple of dozen, it's a big ice shelf, sped up. One of them, I know for a fact, sped up by a factor of 2. It doubled its speed, and it thinned dramatically. So although the breakup of the ice shelf itself didn't add to sea level, it acted like a literal cork in a bottle If you turn a wine bottle on its side, you take the cork out, the wine flows out. The glaciers that feed these ice shelves do the same thing. So that's what I have for you today. Thank you for your attention. Thank you for listening. And I'd be happy to take any questions that you have in the audience or online. Yes, please.
Sí, hola. Buenas. Ya, bueno, durante el proceso de su investigación, ¿cuál fue lo que menos usted esperó encontrar?
What was something that you least expected to find?
¿Cuáles de esos errores
And what of those mistakes of your research would you not repeat again?
I apologize. I turned
Me
off my
disculpo. Oh, you want me to repeat the question? Yes, sure. There's a question of your research. What was one of the things that you least expected to find, that you found, and what were the mistakes that you would not repeat again?
Yeah, those are excellent questions.
Excelentes preguntas.
In terms of the surprising things that we found surprising things almost every day. But some of the bigger ones, I would list two. They were both in Greenland. There are many in Antarctica as we found, but the most charismatic ones, I think you might say, we found in Greenland. One of them was just in the last few years. We flew crisscrosses, hundreds of them across Greenland, north, south, east, west, all over. Tens of thousands of kilometers of flight lines. And with all of those flight lines, we had associated measurements of both not only the surface of the ice, but also the bedrock beneath it. And when a colleague of mine, his name is John Bamber, he's at the University of Bristol in the UK, when he was able to put all that radar data together, and what he found was astonishing. He found a feature that had been buried under the ice that the human race had no idea about prior to 7 or 8 years ago. Think about that. He found a feature, a canyon in the bedrock below the Greenland ice shelf that's roughly the size, actually a little bigger, of the Grand Canyon in the western United States, both bigger and deeper. Completely unknown to man prior to a scientist taking the time to put together the data in a particularly creative way and find it. So again, to me, that's astonishing that something that big, that massive on the surface of our own planet, we didn't even know about prior to just a few years ago. Another one, this one was initially discovered, I believe it was in the year 2013, 2012. We had recently been flying in the southeast of Greenland, but that's an area that has poor weather, and so we were stuck on the ground for a few days waiting for the weather to clear. Meanwhile, a colleague of mine, he had been at a field camp in the same area in the southeast of Greenland, and they were drilling ice cores in that part of Greenland. The purpose of drilling his ice cores in that case was to measure the amount of snow that fell year after year after year. You can measure that by looking at these ice cores, and that's what he was doing. His name was Evan Burgess. And they'd flown him out of that field camp because he was sick. He had the flu. At that time, the flu was kind of going all over Greenland, and he was sick. And so we saw him on the ground, and he had this crazy story he told us. And the story he told was that he was out in this field camp in southeastern Greenland ice sheet, nothing but ice all around him, and they were drilling. And it was, by the way, it was April. It was still quite cold. And they were drilling, and what happened? A gusher. They hit water, and pressurized water. So the water came up, high enough to soak him, to soak his entire camp with liquid water. And they were only drilling a few tens of meters down into the ice. So what they'd found was something that science previously didn't know about. It's called a firn aquifer. A firn is what happens when snow falls on a glacier. Firn describes a continuum between fresh snow on the top and solid ice as it's gradually compressed by the weight of new snow above it. And so it turns out that the thermodynamics of southeast Greenland are such that liquid water can form and persist for years and years, permanently essentially, within those layers of firn. That was totally unknown prior to 2012, completely unknown. But it was found experimentally by Evan and his team, and also our radar. The same year we redirected our own aircraft to map the same area to try to determine the extent of these aquifers. And it turns out they were very extensive. That set off a theoretical race among the theoretical glaciologists and thermodynamicists to explain how this liquid water could exist within an ice sheet. And that came out pretty quickly, as you can imagine. So yeah, the surprises are the best part. That's why we do this. I think your other question, if I remember correctly, was about what mistakes would we not repeat? There are lots. We made a lot of mistakes. So much of what we were doing was brand new, and so we made mistakes and we learned from them every day. And really one of them again was the importance of meteorology. We flew an airplane low to the ice, where our pilots couldn't fly safely unless they could see what they were looking at. We needed light winds, and our instruments also needed a clear view of the ground. And in order to achieve all of those things, you needed a lot of expertise, local expertise in polar meteorology, and that's not something that was fully appreciated. I think the thought at the time was we could just go into the airport's weather office, chat with the local meteorologist, and find out everything we needed to know. And that turned out not to be the case. We needed our own expertise to answer those questions. Your question really scratches the surface of a very broad topic. We could talk about that for hours, but that's the first thing that comes to mind. Any more? Yes.
¿Algo más?
My question right now
Mi pregunta ahora es
related to
relacionado a...
I'm like
Yo soy como
one step away
un
from
paso...
choosing what kind of engineering I'm going to take, if it is electrical, mechanical, or maybe software engineering, and what can be a really great advice of what I want to choose. Because you told in this talk that there were many skills that you had to learn on the go. Many things that maybe with your degree you didn't know, you didn't even have to, you didn't know that you had to learn them until you get there. And parallel to that, I am learning quantum computing. A very important tool that it can, you said trips like from Santiago to Iquique, from Los Angeles to New York. This powerful tool can make things 10 times easier, and I'm eager to learn a lot about this. And well, it's a lot to process, but if you could guide me in some way, I would be very thankful.
Yeah, I'd be happy to. Those are good questions. First of all, I'm glad you're here, and I'm glad you're studying what you're studying, because our species needs people like you. Obviously, you know that. You know how important your topic is. In terms of giving you advice on fields, I would probably give you two pieces of advice, and they're somewhat in conflict with each other. So just be aware of that up front, but I think you can resolve this on your own. The first thing and the most important thing is anything that you do in your life that you're going to do for a long time, for years, in your case decades, it's got to be something you're passionate about, something that you enjoy, and something that you feel strongly about. So the most important thing you can do at your age particularly is to pick something that interests you very deeply and that you think will continue to interest you for decades to come. Because if you don't, you're not going to stick with it and you won't be as effective with it. That's number one. The second thing is somewhat at odds with that. So let me maybe try to explain that. You're going to have to figure this out for yourself, as you know already. But the second thing is that I studied aerospace engineering in university, and to some degree, well, that treated me very well, but I was very lucky. I think the advice I would give to most people would have been to study something of a little more general applicability, such as electrical engineering or maybe mechanical engineering. And the reason is, I think you saw from my talk, the reason is because you will be called upon to do things that you never expected you would do. And so studying a field, another one is physics, by the way, chemistry. Some of the more basic, generally applicable topics are, in many ways, I think are going to serve you best in your career to come, because it will prepare you for a much broader array of problems that you might solve. And again, that's somewhat at odds with picking the thing that you're passionate about. It may not be mechanical engineering. It may not be a generalized topic like that. But that's going to be up to you to figure out.
Thank you very much. And One thing that many of my classmates from my faculty are talking about is aerospace engineering. It's not currently available, but many of them are looking forward to study overseas, or maybe compatibilize many of their bachelor's or other kind of degrees towards that, maybe, in hopes of working with NASA or for NASA.
Yeah, in that case, if the universities which are, well, most available to you, local universities, if they don't offer a program in aeronautical engineering, I would certainly suggest mechanical engineering. It's the closest thing to it. However, as you know, in modern life, electronics are not going away. So electrical engineering or computer engineering are also gonna treat you very well in coming times. But if you really want to understand things like thermodynamics, rocket engines, the way air flows over a wing, how to make an airplane stable or unstable, mechanical engineering is probably the best choice. I would say, however, that aeronautical and aerospace engineering topics are very widely available in the United States. Many universities offer those programs, and they're happy to have talented students from abroad.
Great.
Anybody else in the audience? Thank you for typing them in English. Okay, the first question. Mr. Sonntag, considering your extensive experience in polar and glaciological research, especially with Operation Icebridge, could you share your perspective on how advances in remote sensing technologies have transformed our understanding of the impacts of climate change in the polar regions? Additionally, how do you envision these technologies evolving over the next decade to improve our understanding and response to global climate challenges? Well, when I started my career, global warming wasn't cool, I think is the best way I could put it. It wasn't widely discussed. It wasn't a big topic of interest. So when we started out doing what we did, we had to beg for the resources to do it. Getting money to fly airplanes over Greenland is an expensive proposition. And so in order to get NASA to commit resources, the US government to commit resources to doing that, we essentially needed brave people. He was a British emigre. His name was Bob Thomas. He sadly passed away now. He was one of my early mentors in my career. He started out his life in the British Antarctic Survey and later moved to the United States and worked for a while as a program manager at NASA headquarters. In NASA, a program manager is the person who identifies research needs. He or she look for the topics that are most in need of study and most in need of resources. And so it's a very important job. They guide resources into fields of study. And Bob, he met my boss, and who were people of very different fields. They're very different in every way, really. But they just happened to meet at a conference one time. That's why you go to conferences, because you make connections that you don't expect and that lead to very productive things. Bob was a very brave guy. To approach NASA headquarters in the early 1990s and request several $1 million to send an airplane to Greenland with all these technologies that you'd never heard of to collect data about a problem you didn't know existed was a hard sell, a very hard sell. But Bob was a brave guy. I think one of my slides I mentioned the word bold in it, and Bob's a good example of someone who was bold. He really went out on a limb because before most other people, he saw the nature of the problem that we're facing with climate change, how the world's great ice sheets are connected with that problem, and he thought he identified a technology that might help to address that problem. And he convinced his bosses, at the risk of his own career, to make that investment, and it turned out, obviously, to work pretty well. So that's part of the answer to that question. I think let me look and see what else. I know how do you envision these technologies evolving over the next decade or so? So there's a fairly obvious one, and in fact, it was fairly obvious 10 years ago, but this is one of those cases where technology actually moved a little slower than we thought. So when we started Operation Icebridge in 2009, it was in our charter to move as quickly as we could to unmanned aircraft, unpeopled aircraft, I believe is the current term. And that was because at the time, the United States, mainly in the military, had developed some very large, very expensive drones that cost millions of dollars a piece, but that could fly a very, very long time. They didn't burn nearly as much fuel as we did, and the thought was they would be, because you didn't have people on board them, they would be much cheaper to operate than the airplanes that you saw photos of here that we used. So within literally a year or two of 2009, we were supposed to move entirely to these unmanned systems. Well, that turned out to be not feasible at the time. And the main reason it wasn't feasible was economics. It turned out that not having people on the plane didn't save any money at all. In fact, it cost more money mainly because in order to fly these unmanned, unpeopled aircraft safely and productively, it took more people on the ground to making sure that could happen than it actually would have to put them in the airplane itself. But that technology is finally changing now. You can do a lot with small drones that we couldn't dream of even as recently as 10 years ago. So in terms of what happens in the near future, I think remote sensing of ice sheets from aircraft and satellites, as well as in situ observations from field teams actually going out and living on the ice, as Charlie Bentley did, those are going to continue to be vital. Let me back up from that and mention that spacecraft measuring ice sheets from orbit gives you the big picture. But they also zoom out, if you know what I mean by that. You don't see a lot of detail. So putting people on the ground who can provide that detail for very limited areas is important to contextualize, to develop a broader understanding of what the satellites are telling you. And aircraft fill a middle niche. For example, right now we do not have the technology to measure ice depth, the thickness of the ice from orbit. But we can measure it on the ground, and we can measure it from aircraft. So moving that technology to drones is, I think we're at a point now where that is going to save a lot of money and more importantly, make the technology and make the science more accessible to everybody. And in fact, I have some colleagues at the University of Kansas who are working on that right now. They've done that in Greenland a couple times, and I believe right now, come to think of it, they have a drone deployed near the South Pole, prepared to collect some of that data. We have a lot to learn, but that would be the first thing I would think of when it comes to new technology helping this problem. The second question, what difficulties have you had during your explorations? What has caught your attention that you didn't expect? What interest and/or strategies exist regarding the different riches found in Antarctica? Boy, that's a great question. And what the future missions consist of. So I think the first two parts of that, I think my talk probably addressed. Now, there's a tough one here. What interest and/or strategies exist regarding the different riches, mineral riches found in Antarctica is the question they're asking about. It's not a topic I'm terribly knowledgeable about, so I'll limit my comments to a few. There was a treaty adopted. And again, I'm not an expert. I believe it was adopted in 1978 called the Antarctic Treaty. Chile is a signatory to that treaty, as is the United States. And most of the major countries in the world are signatories to the Antarctic Treaty. And the Antarctic Treaty was way ahead of its time. The purpose of the treaty was to set aside Antarctica as essentially a scientific research bastion. It was supposed to not be exploited economically. I wonder if maybe somebody has some knowledge about that. Oh, gotcha. Okay, good. I was actually hoping you did have some more knowledge because I'm speaking a little bit off the cuff here. Anyway, that treaty has been successful for the 40 or so years since then, 45 years, I guess that is, at keeping economic exploitation out of Antarctica. My personal feeling is that won't last forever. Money talks, and as soon as valuable things are found in Antarctica, and more importantly, more relevantly, economically viable means are developed to extract those resources, I think the Antarctic Treaty is going to become a much harder legal concept to enforce, and that's something that your generation will be dealing with more than mine. I'll be retired by then, but something to be aware of for sure. Any more questions on that topic? Sorry to embarrass you. Any more questions on that topic while we're on it? Okay. The third question, when it comes to media generated from science, such as documentaries, YouTube videos, blog posts, news articles, how do you think they affect the public's perception of science? they do affect the public's perception of science. This is something I started out my career being pretty skeptical of. When I started, of course, we didn't have social media and that sort of thing. We did documentaries, of course, films, and the rise of social media has had a big impact on the work that we do. NASA, my agency, or the agency I used to work for anyway, is, I think it's fair to say NASA is feared by the rest of the other agencies in the United States government, because NASA has taken this particular aspect of its work more seriously than anybody else. NASA's good at selling itself, is another way to put that. And NASA also has an easy product to sell. Unlike most government agencies, NASA doesn't regulate anybody. They don't tell people what they can and they can't do. And that naturally gives us a natural leg up in popularity with somebody like the EPA. Because the work we do is pretty much strictly positive. The sell we have to make is that we do suck up a fair amount of money from things that could be used for other things. And that's where documentaries, films, YouTube, social media come in. And NASA does take that very seriously. I mentioned before that NASA would not send a meteorologist with us. It was hard to get them to send an electronics technician with us, but they would send documentary filmmakers with us. They would send social media specialists with us. So NASA takes that very, very seriously. I think NASA has been really quite successful at that. And again, I mentioned the fear that the other federal agencies have in the United States about NASA's prowess in that regard, and I think that shows that NASA has been very effective in that regard. However, I would say that some of you, some of the students who may be listening, for instance, one of the most able people I ever encountered in my NASA career was a woman named Emily Schaller, and Emily had a PhD in astrophysics. She was one of the smartest people I've ever met. But her job at NASA didn't involve that. Her job at NASA was strictly involved in outreach. So one of the things she did was she led an internship program that brought about 30 students, college students, university students, in for a NASA airborne program where they actually flew on a NASA aircraft in Southern California. And it was a 6-week program. They spent half of the summer in Southern California. Part of it flying with NASA, designing their experiments, helping to build the instruments, and then processing the data and then presenting it. That program, it's called Student Airborne Research Program, SARP. Emily was in charge of that program for up until quite recently. And Emily had a gigantic impact on NASA's workforce, and I know for sure on the individual students involved. The accolades that we hear for over a decade now, but the students who were involved in that program, they just speak glowingly of it. It changed their lives, and you hear that over and over and over again. So I guess my point is similar to the point I was making earlier. Keep your minds open. It may turn out that you don't like astrophysics as much as you thought you did, or I hope you do, but you may not. But you might find yourself being very adept at social media, and there's a role for that, an important role for that. Question 4, what discoveries led you to continue exploring Antarctica with such impetus, that's a good word, for so many years, if you could highlight any of them. I'm a little hesitant to use this term, but I'll use it anyway because I think it's apt. I showed you that picture earlier. In fact, I'll bring it up again. Pine Island Glacier. Incidentally, in case you're curious, why does it have that name? It's a strange name for a glacier in Antarctica that's not on an island and has no pine trees anywhere near it. It's called that because it was originally mapped and probably discovered, for that matter, by a seaplane launched in 1947 from a U.S. Navy ship called the USS Pine Island. That's where the name came from. Fun story, one of the first pilots that we ever had for NASA Operation Icebridge, he was formerly Air Force. He worked for NASA by then, but he was formerly an Air Force pilot. And when he was a young man, when he was a young lieutenant with the U.S. Air Force, the U.S. military, and I would imagine the Chilean military too, does a lot of exchange programs where naval officers will spend time with the Army and Air Force will spend time with the Navy and that sort of thing. And his name was Bill Brockett, and he spent some of his early years in the military on board the USS Pine Island in the 1960s, little knowing that 50 years later he'd be flying over Pine Island Glacier, having spent time on the ship that discovered it all those years before. Anyway, I think I digressed a little bit. So Pine Island Glacier is in West Antarctica. Its neighbor is called Thwaites Glacier. That turns out to be an extremely relevant place to study. When we started working with your country in 2002 with the Armada and with the CECS, it was generally known from Charlie Bentley's work and also from others that most of the West Antarctic ice sheet was bedded under sea level. In fact, the ice sheet was so thick that it sat on bedrock that was below sea level. And that makes it a marine ice sheet. It's what the scientists call it. And what that means is the ice sheet is in close proximity to the oceans and both is affected by the oceans and affects the oceans. What we were only beginning to learn in 2002 was that not only was the bedrock below sea level, but it slopes deeper inland. It slopes deeper as you move inland. It's a little hard concept to get your mind around because normally when you walk, you start at the waterline on a beach, you're walking up a hill, right? In Antarctica, below Pine Island and Thwaites Glaciers, below that point right there, the ice actually gets deep. The rock, the bedrock, the soil, you might say, gets deeper as you move inland. Why is that important? Well, if a glacier sits on a mountain and the glacier is in contact with the oceans and the ocean's warm, that glacier could be expected, just by common sense, to thin, to melt where it's in contact with the ocean. And it will eventually retreat to a point where it's above the ocean. It's not in contact with it anymore. At that point, it stabilizes. Kind of makes sense, right? The problem with Pine Island and Thwaites glaciers and many of the other glaciers in West Antarctica is that can't happen because the more they retreat, the more they come into contact with the ocean because that bedrock gets deeper and deeper and deeper as you move inland. That is societally of prime importance because it means that there is a positive feedback mechanism. Positive is usually a good word. In this case, it's a bad word. It's a runaway phenomenon. The more those glaciers melt, the more they're going to melt. And the more they're going to affect places like Viña del Mar and New York and Tokyo and populations all over the world, whether or not they're in contact with sea level. And in fact, this is the word that I was hesitant to use. Many scientists are hesitant to use it, but I'll use it anyway because I think it's correct. Journalists use this more often, and the word is the Doomsday Glacier. Thwaites Glacier, which is just about 100 miles west of the point where this photo was taken, has been often called the Doomsday Glacier because it has that bedrock that slopes inland. It's huge. Thwaites Glacier is so big you can't even see it all in one view from our aircraft, and it took us about 15 to 20 minutes at jet airliner speeds to fly across the width of it. It's enormous. And we know it's thinning. It's already lost most of its floating tongue, and it's continuing to thin. We know that because we've been measuring it. And again, the more that glacier thins, the more it's going to thin because the more it's going to come into contact with this warm ocean water. That's why they call it the Doomsday Glacier. And that's my answer to the question. These are not abstract topics. These aren't questions these aren't problems in search of these aren't solutions in search of a problem. These are problems that will affect all of us, and they'll especially affect our children and our grandchildren. So it's not hard to be motivated to study something like that. I think that's my answer to the question. The fifth question, do you believe that science will become the objective of a society? Will there ever be a viable scientific government? Again, that's fairly outside my expertise. Not fairly, it's completely outside my expertise. It's been talked about for many years. A lot of science fiction writers in the English language, and I would imagine the Spanish language too, have addressed that topic. Isaac Asimov, maybe most relevantly in the English language. I've known a lot of scientists. I'm not even sure that's a great idea, to be honest. Scientists are just people. They're like everybody else. They have the same foibles and the same weaknesses and the same strengths that anybody has. So I don't know that, that scientists are any more qualified to lead a population than anybody else does. What I do hope is that science will more inform public policy decisions than they do now. In the United States, we're pretty lucky, and I think in Chile you are too. Your governments and my government are still forward, at least for now, are forward thinking enough that they do invest a lot of resources in science and in understanding, providing direct information to understand our planet that we live on, and also providing information that will help us make better decisions well into the future. So yeah, I do think we're partway there already, and I do hope, as I think many of you do, that we'll continue in that path, but maybe not all the way to a scientific government. And then the last question, What was the experience of performing the flyover given the weather conditions and electromagnetic waves of the place? Well, interesting question. So I've already addressed the weather part of that. When you fly an airplane packed with scientific instruments that are all emitting all kinds of radiation, not the unsafe kind of radiation, by the way, it's not ionizing radiation, but radio waves, light waves from lasers, all kinds of things like that, you have to generally pass a lot of regulatory approvals to make those kinds of flights. That was less true in Antarctica, but there's no government in Antarctica. Again, it's a scientific preserve. But in places like Greenland, Alaska, Svalbard, other places we fly, these places do have their governments, and understandably, they don't want you interfering with their radio stations. They don't want you, another thing we ran into is we had to prove we couldn't blind a whale if we happened to fly over a whale with our laser. I don't want to blind a whale, you know, but we had to actually technically prove that it turned out that given if you calculate the amount of energy in a given laser shot, a single laser shot wouldn't blind a whale. We could prove that. We did find out that 2 laser shots would, if they came in close succession. We made a very detailed study of this. We had to pass the regulatory approval. And we found that 2 laser shots in close succession could indeed blind a whale. Nobody wants to blind a whale. But what we showed was because of the geometry in which our laser scanned, we actually couldn't hit the whale twice with 2 consecutive laser shots. That's the kind of thing you have to worry about when you're worried about the electromagnetic spectrum and doing science operations within that. So I think that's all we have. I'd be happy to take any other questions that any of you might have. And if not, thank you very much. Thank you for coming. Thank you for your attention.
Muchas gracias, Profesor John Sonntag, por su
for your talk, this dialogue you offered today in joint work with the U.S. Embassy. So we would like to thank you all for joining, and to whoever follow us on our YouTube page. Thank you very much.